spaceships' designs and electromagnetic compatibility, the important concept of immunity. Susceptibility, respond to unwanted electromagnetic energy. This is a negative behavior that we have to alter. During this process, emission and interference are also conditions that should be controlled, in order to reach a state of immunity, that is characterizes the electronic unit condition, which is satisfactory without materials degradation. Immunity is always important for spaceships' designs and in a broader sense of scope. A noise voltage causes improper operation of a circuit, and interference. Noise cannot be eliminated, in absolute measurement term, but interference can, until it no longer causes interference. The effective function of filtering depends on the source and load impedances, between which the filter is working. Filtering is done in software with the use of peak detectors. Biot-Savart law relates magnetic fields to the currents which are their sources. The common mode rejection ratio CMRR is a metric to quantify the degree of the effectiveness of a balanced circuit in rejecting common mode noise voltages. The overall design goal and theoretical conception is the immunity of the device's material structures and operations for electronic circuitry. Electromagnetic compatibility in transmission lines. Transmission lines guide the electromagnetic energy, and can be classified by their geometry. Some common transmission line geometries are coax, microstrip, stripline, balanced line, waveguide. Remember, the dielectric is the key, not the conductor, because from the dielectric the electromagnetic energy is propagated, and the medium of propagation for most of the cases is the air. So, the electromagnetic compatibility between internal and external, into the vacuum, electronics components requires a quite different designs materials considerations, including the configuration of ground shielding. Electromagnetic compatibility in transmission lines. For both internal and external electronics of a spaceship, another design performance consideration is the transmission line velocity of the propagated electromagnetic energy that is given by velocity of propagation is equal to the speed of light divided by the square root of the relative dielectric constant, in which the medium is propagated. Where c is the speed of light in a vacuum-free space, and r is the relative dielectric constant of the medium through which the wave is being propagated. The larger the dielectric constant, the slower the velocity of propagation will be. Electromagnetic compatibility important considerations. Dielectrics and transmission lines, the velocity of propagation is 1/2 the speed of light in a vacuum, therefore the speed at which a signal propagates down a transmission line will be about 6 inches per nanosecond. Propagation rate. It is important to note that what travels at, or close to, the speed of light on a transmission line is the electromagnetic energy, which is in the dielectric material, not the electrons in the conductors. Electromagnetic compatibility and wave fields. The relative magnitude between the magnetic H field and the electric E field depends upon how far away the wave is from its source, and on the nature of the generating source itself. The ratio of E to H is called the wave impedance, ZW. If the source has high current and low voltage, the near field is predominantly magnetic. If the source has low current and high voltage, the near field is predominantly electric. The space surrounding a source of radiation can be divided into two regions, the near field and the far field. The transition from near to far field occurs at a distance of wavelength divided by 2 pi. Electromagnetic compatibility. For a plane wave in the far field, ZO is also equal to the wave impedance ZW. For these conditions on insulators, the characteristic impedance is independent of frequency. Inductance L is only a function of the dielectric constant and the characteristic impedance of the line. Here is for the capacitance C. Transmission lines that have the same characteristic impedance and dielectric material will have the same inductance and capacitance per unit length regardless of the size, geometry, or construction of the line. Electromagnetic compatibility and materials issues. Most metals have an intrinsic impedance of only milliohms. For low impedance fields H dominant, less energy is reflected, and more is absorbed, because the metal is more closely matched to the impedance of the field. This is why it is so difficult to shield against magnetic fields. On the other hand, the wave impedance of electric fields is high, so most of the energy can be reflected. Thickness plays an important role in shielding. When skin depth is considered, it turns out that thickness is only critical at low frequencies. At high frequencies, even metal foils are effective shields. Electromagnetic compatibility and materials issues. There are many ionization sources that affecting the bonding state, the structure and the electronics conditions. Galvanic corrosion for metals. Bi-accelerated electrons, sometimes even from the same instrument functionality. Bi-discharged ions, further gas ionizations, emitted from anode, fields more than 20 kV per minute. Bi-photons, from recombination processes, from the environment like the sun, other discharges and other radioactivity of construction materials. But everything is changing if any of the following varies, like field geometry, temperature, gas mixture, particular humidity, contact material. Paschen is known because he controlled all the variables that would have destroyed his systematic results. The Paschen curve, in a way, don't go to high vacuum. But we assumed that the air measurements could reveal probabilities for vacuum operations. The Paschen minimum can warn us for hazards on test units. Note, if we extend the Paschen curve for high vacuum, pressure is too low for the gas ionization effects. Your basics in brief. Noise cannot be eliminated, in absolute measurement term, but interference can, until it no longer causes interference. The dielectric is the key, not the conductor, because from the dielectric the electromagnetic energy is propagated, and the medium of propagation for most of the cases is the air. The electromagnetic compatibility between internal and external into the vacuum electronics components requires a quite different designs materials considerations, including the configuration of ground shielding. The larger the dielectric constant, the slower the velocity of propagation will be. It is important to note that what travels at, or close to, the speed of light on a transmission line is the electromagnetic energy, which is in the dielectric material, not the electrons in the conductors. Thickness plays an important role in shielding. When skin depth is considered, it turns out that thickness is only critical at low frequencies. At high frequencies, even metal foils are effective shields. If we extend the Paschen curve for high vacuum, pressure is too low for the gas ionization effects.